Hey guys! So today I'll be walking you through the calculator math section of College Board's first SAT practice test. Before we get into it, I just wanted to say that this video is sponsored by Prep Scholar. Prep Scholar is the test prep company that helped me to score 1600 on my SAT. Their program includes a really helpful bank of practice questions and videos that walk you through all the SAT topics you'll need. So if you're interested in a paid tutoring service, I definitely recommend checking them out. If you use the link in the description below and end up purchasing their program, I'll get a small commission from that, which will really help the channel out. Thanks for listening, and let's get into it. John runs at different speeds as a part of his training program. The graph shows his target heart rate at different times during his workout. On which interval is the target heart rate strictly increasing and then strictly decreasing? So this is a graph of his target heart rate over time. So the slope of this graph over these intervals will show it increasing, staying constant, or decreasing with time. We're looking for when it strictly increases and then strictly decreases only. So we're looking for a pattern kind of like this, not any horizontal lines. So between 0 and 30 minutes, we see a horizontal line there where the heart rate stays constant. Between 40 and 60, this is what we're looking for here. It just strictly increases and then strictly decreases. Then the other two, between 50 and 65, we see that is a constant slope. And between 70 and 90, we also have a constant slope. So B is our answer. So if y equals kx where k is a constant, and y equals 24 when x equals 6, what is y when x is 5? So first let's solve for this constant k. So we have when y equals 24, x is 6. So that would mean k is 4 if we divide both sides by 6. Now we can plug that 4 in for k for our equation. And when x is 5, we're looking for y. So we can just plug in a 5 for x, and we get 20 is y. And the first one is kind of difficult to check in a different way because it's just analyzing a graph. This one I would suggest just plugging in the 20 back to this equation and then making sure you solve for k correctly. So we have lines L and M are parallel in this one, and S and T are also parallel. If angle 1 is 35, what is the measure of 2? So when we have parallel intersecting lines like this, we know that all of these angles and all of these angles are going to be equal to each other. So all of those will be 1. That's just like a property of intersecting and parallel lines. We can treat this like it's angle 1. And we're looking for the measure of angle 2. We have a setup kind of like this now. And we know that this is 35. We know that the entire line is going to be 180 degrees. So to get angle 2, we can just do 180 minus 35. That'd be 145, I'm guessing. We can check with our calculator though. The double check for this one would just be looking at this. We know that angle 2 isn't going to be less than 90 degrees because that is way greater than 90 degrees. That's our only answer that's greater than 90, so we're good. All right, now we have a little tricky word problem set up. So if 16 plus 4x is 10 more than 14, what is the value of 8x? Now this one can get confusing. You just got to think it through carefully. So we have 16 plus 4x is going to be on one side of our equation, and we know that that's 10 more than 14. So you want to make sure you're adding the 10 to the right side. 10 more than 14 is just 24. So we can just treat the other side like it's 24. Now we have our equation and we can solve for 8x. And the way to do this could be subtracting both sides by 16. So 4x is 8. And then instead of solving for x here, we can just multiply this entire thing by 2 and get 8x equals 16. And to double check ourselves, let's just make sure we set this 10 up on the right side because that's where this would go wrong. So we know that 16 plus 4x is 10 more than 14. So this side is greater than 14. So to get this side and this side equal to each other, we would have to add more to the 14, which is why we add 10 to that side. That's still sometimes a little confusing to me when setting these ones up. Just make sure it makes sense in your head. Now, which of the following graphs best shows a strong negative association between D and T? So this one's also just kind of like a statistics type question. If they're looking for a strong association, it's going to mean that all of these data points are going to be clumped closer together. And a negative association just means a negative slope. So it should look like that as opposed to that. That would be a positive slope. So we're looking for a negative association with all the dots kind of centered around that line pretty closely. And the one that matches that is D. This one's also a trickier one to check yourself on, just because it's about a statistics concept that you either kind of know or you don't. Now we have a units question. A hospital stores one type of medicine in 2 decagram containers. Based on the information given in the box above, how many 1 milligram doses are there in one 2 decagram container? So we can use dimensional analysis for this. So if we have a 2 decagram container to start with, that's what we're given, and we can just say over 1 for that. Then to convert to milligrams, in order to cancel, we need the decagrams on the bottom. First, let's convert from decagrams to grams, and then we can convert from grams to milligrams. So we can do decagrams to grams, we have 10 grams on that side, 1 decagram on that side. So there's 10 grams for every 1 decagram. We do the same thing with grams and milligrams. So we have 1 gram for every 1,000 milligrams. And if we cancel out everything that we just wrote, as it can cancel, we'll be left with an answer in milligrams. So our denominators are just multiplying by 1. Our numerators, we have a 2 times 10 times 1,000. So that would be an answer of 20,000 milligrams. And to check ourselves on this one, think of how small a milligram is, and a decagram is like a larger container. We know it's 10 grams. It would make sense that there are a lot of 1 milligram doses within a 2 decagram container. So this answer makes sense realistically. Now we have the number of rooftops with solar panel installations in 5 cities is shown in the graph above. If the total number of installations is 27,500, what is an appropriate label for the vertical axis of the graph? And looking at these answers, it's always going to be the number of installations. It's just a matter of what our scale is here. I think it would make sense, since we know that this is some kind of number of installations, to count the total number that we have. So in city A, we have 9 plus 5 plus 6 for city C plus 4 for city D and plus 3.5 for city E. And guess what? We probably know that number is going to be 27.5. Let's just plug it in on our calculator to be sure. So that gives us 27.5, which is kind of to be expected. If we have 27.5 as our total number, and we need to get that to be 27,500, how much would we have to move the decimal place, basically? If we move it 3 decimal places, we would get 27.5 to 27,500. And 3 decimal places, that's just the equivalent of multiplying by 1,000. So we know the number of installations is going to be in the thousands of installations. And to check this, maybe I would just do that again, maybe divide it on a calculator just to be sure. So if we have like 27,500 and we need 27.5, how many we have? We do get 1,000. Okay, now this is kind of a fun one regarding absolute value. For what value of n is the absolute value of n minus 1 plus 1 equal to 0? This might be one where you're not sure exactly where to start, but if in doubt, always just try to rearrange. So maybe let's try to solve for n. We subtract both sides by 1. We're left in a scary situation here, because the one main rule about absolute values is that they're always positive. It's like the distance away from 0 on the number line, but that's always going to be a positive value. So right now we have the absolute value of this on its own is equal to -1, which that can't exist. So we know that from this that there's no value of n that will equal to 0. Just think about it. There's no value that we could plug in here to get a negative answer if these absolute value lines are always going to make the final answer positive. So that's like our double check for that one, I guess. Just kind of a theoretical question. Now we have these famous 2-part problems, and I don't know if they really exist on the non-calculator section, but they're a big thing here. These will usually be in reference to some random equation that they give you, and the first part is usually solving this equation for a different one of the variables, so just rearranging things. Then the second one is more like applying the formula to something. Of course, that's not always the case, but usually it's something like that. So we have the speed of a sound wave in air depends on the air temperature. Formula above shows the relationship between A, the speed of sound of a wave, in feet per second, and T, the air temperature, in degrees Fahrenheit. So which of the following expresses the air temperature in terms of the speed of a sound wave? So we don't really have to comprehend exactly what the equation is trying to tell us right now, we just have to solve for T. So if we start with A equals this, our original up here, we can subtract both sides by 1052 to get that 1.08 t alone, and then divide by that. And then, so we get t equals a minus 1052 over 1.08. And does that match with anything? Yes, it looks like it matches with the first one. And to check this, maybe try solving this for a again to see if you get the same as the first equation. Usually this first part will make the second part easier, but if you're not confident you did the first part right, you can also just use the original to solve for the second part. So here we have, at which of the following air temperatures will the speed of sound be closest to 1,000 feet per second? Remember, a is going to be our speed of sound, so that's going to be the 1,000 feet per second value, and the air temperature is going to be T. So we're looking for T here. So it would make the most sense to use the equation that we just solved for. So T equals a minus 1052 over 1.08. And then if we plug in a equals 1,000, we get, here's where our calculator comes in very handy. This would be kind of a nightmare to do by hand. So we have 1,000 minus 1,052, then divide that by 108. And that gets us about negative 48 degrees, which is one of our answers. And to check this, you can plug in negative 48 to either of these equations and see if you get a value close to 1,000 feet per second. But we're not going to do that for time's sake. Alright, since the math calculator section is so long, I'm going to split this up into 5 different parts. The second part will be released next week. Until then, thanks for watching, be sure to like and subscribe, and see you soon!